And then I guess we're going. Right. What I was thinking to do today, and this is the basic final, I guess it is the final taught session, was kind of to go back over what I did last week, but hopefully with the benefit of what we did on Friday, it will sort of make a little bit more sense. So what I was going to do was to get the CP2K input and output that I had before, and then adapt it to run maybe a little block of silicon or something like that, give you a couple of sort of example templates of using the DFT, but maybe sort of particularly once we run them to have a bit of a look through what's going on there and the different bits that are going through and see if we can link it into the theory of the DFT. So rather than a lot of it there will be still quite a string of numbers and stuff, but hopefully the main sections we can at least sort of boil down to bits of the theory that we looked at. There's a couple of bits of extra theory we haven't really touched on that I think we'll leave aside and leave as a bit black boxy for now. And I should say there are going to be assessments released later this week. I need to check with Manuela, but essentially they are going to be based around, so in nanophysics it will be based around a question on stuff you did with Andre and one on the DFT, and it will be kind of what we're doing here to some extent, mainly as in explain the steps in a DFT calculation. And for molecular modelling, I'm going to ask you to run some DFT calculations on some materials, or, and I'll show you in a second, there's new developments in materials modelling. So we'll be on the bleeding edge. People have started actually putting data into online databases, which you can then access, and then so essentially you can get the results of calculations that other people have run and use them to sort of analyse and do data. So it may be beneficial to sort of, if you've got everything set up, to run some of the calculations yourself. But on the other hand, there will be an alternative that you can access stuff online. And it might be of interest to some of you to have a play around with it, sort of explore some bits and pieces. Does that sound like a sort of reasonable overview of things? Any questions?
Yeah, that sounds fine.
Okie dokie. So where shall I go first? Let's go back to the inputs. So I'm in my Linux environment, and I think my calculation was this system called let's get rid of all the cruft. So I've got my input file for CP2K, and this was for a hydrogen molecule, which is 2 atoms of hydrogen bonded together. So there are a bunch of technical settings that we largely can ignore. That's a default. It's a default. That will keep. Right. So there's two technical things here. I should put a commented file about this. So there's the basis set. This is used to convert to a linear algebra problem. So we have our Schrödinger equation, which in DFT theory gets converted to this cone-sham set of equations. And then you need to do integrals of wave functions, your Hamiltonian wave functions. And you need some way of describing your wave functions numerically. So you split them up into some expansion of some functions that you can use. So a bit like doing a sort of a Fourier analysis, if you like. So you could break up a wave function into a certain number of sine and cosine waves going across your box. CP2K actually uses something different. It uses Gaussians centered on the atoms, so they look a little bit like the solutions to an atomic problem. And if you add up enough of those, you can represent most wave functions fairly accurately as some linear combination of different basis functions. And so in a couple of places in this input file, there's places that specify which number of Gaussians to place on which atoms. Other codes, and if you go back to the tutorial on DFT, the website, you'll find they're using a different code that tends to use so-called plane waves, which really are these sines and cosines. And you can expand, they're actually a complete basis set, so you can expand any reasonable density in a certain number of those. There's a potential which defines the electron nuclei interaction. So again, for technical reasons, we don't tend to have the full point charge at the nuclei. There's some effective interaction between the electrons and the nuclei that in the atomic case leads to the same set of the same energy states for the atom, and it just makes the problem more tractable. Again, can go into details, but for now, to define our model, we've got these sort of technical parameters in terms of the basis set of potential, and they do adjust the Hamiltonian so that the full problem we're solving. The rest of these parameters here, multi-grid, let's just ignore for now. It's a CP2K specific subtlety. There's SCS, so this is how numerically accurately we find the minimum energy of the electrons. So how accurately we determine this density and associated energy of the system. So this is just how we put in a guess density and let it evolve through a series of iterations until we find the minimum electronic energy of the system subject to where the atoms are. So these are technical parameters to optimize or minimize the electronic energy in that SCF section. So SCF stands for self-consistent field, so it's where the Hamiltonian, which includes the electrostatic interactions, the average electrostatic interactions of the electrons, becomes self-consistent in the sense that the density and then the potential that you put in is the same that one comes out at the other end.
Matt, can I just check that the basis set and the potential, are they separate files within the directory then?
They are, yes.
Same, yeah. So it's just pointing to them.
So those two settings here, I'll get me pointer actually, just so I'm less likely to lose track of where I am as well. Yeah. So these things just tell CP2K where to look for a file that actually then contains the information. So the basis set will then contain for sort of if it's atom type lithium, then put this number of Gaussians with these exponents on the thing for converting it to a linear algebra problem. Yeah, so this bit just tells it which files to look in. Now
and the SCF is the parameters are actually within the file, it's within the import file itself.
So the basis set and the potential are just defining those. These things here are setting up technical bits about solving this nonlinear differential numerical differential equation. So there's lots of sort of words here. Exchange correlation. This defines the density functional that is used. Now, its Parde is local density approximation. So you may remember that the simplest density functional was based on this homogeneous electron gas. So you've got just a uniform electron gas. If you scale its density, the energy per volume changes because the electrons are interacting in this model. So if you increase the density, there's a non-linear change in the energy as you put more electrons in because they're getting denser. The electrons on average are getting closer together. So there's various changes in the energy as a function of this density. And what we do once we found our density, or when we're finding it, is we sort of essentially cut it up into little cubes, see how much electron or what the density of the electrons are in that cube, and we assign it the equivalent energy that a cube of homogeneous electron gas would have. I think I mentioned that for the electron gas, we can't do a pen and paper complete solution for the exact energy of the electron gas, but you can do a numerical, in fact a Monte Carlo essentially, simulation of the electron gas and get a very accurate energy as a function of the density. And this Parde thing, as it's called in CP2K, is a analytical function that fits that data essentially. So it's an analytical fit to the energy per density. There could be other ones. I could have I could change it to say PBE, which is a generalized gradient approximation. Other things. I could change which density function I'm using in there. So that, again, along with, so this is perhaps a bit more fundamental. This is the most fundamental setting of our model. Once we've set the density functional and where the atoms are, in principle, we've set up the problem, but then we need to put in additional parameters to actually allow us to solve it on the computer. So the first thing we then put in is our basis sets. So we're transforming from a sort of algebraic problem in terms of just a wave function to defining the wave function as a sort of a vector in terms of how much of this basis function, how much of that basis function. So we convert from a sort of a continuous wave function to a vector in terms of how much each of those basis functions is involved. And then by adding up the contribution of each basis function, we can actually recreate the wave function as an actual function of position. Does that make any sense? But I'll provide this, and people can come back ideally in this Teams chat and sort of ask questions on details, and we can reiterate it. So within, this is all within the DFT section. So this is defining our density functional. And the last bit I've got here is a print section. I'm printing out the electron density of the system. And it's based on those little cubes that we used essentially to define this exchange. So we print out how much density is in each cube, and then VMD can take that information and convert it into things to actually visualize. And the MO cubes, so this prints out the 1 electron wave functions, the set of 1 electron functions that go into our Slater determinant that build up the many electron wave function, which builds up our electron density. So essentially this electron density is going to end up being the sum of the squares of all of the wave functions that are occupied. So we solve for our electronic levels. We put 2 electrons, up to 2 electrons into each state from the bottom up until we're filled up. And then to get a density, we take the square of each of these wave functions, add them up, and that gives us our electron density. And so we're going to print those out so we can look at them if we want. This is 1 electron states, and this is total electronic density, and this is number of unoccupied states. So if you think back to I don't know, sort of Balmer series, this UV lamp that you're shining at various noble gases, and you get these line, or at hydrogen or whatever, and you get this series of absorption lines where the photon has come in and excited an electron from an occupied state up to a state that was previously unoccupied. When we do the density functional calculation, in principle, we can also calculate the unoccupied states. So we get the ground state density from the filled occupied energy levels, and then we can get unoccupied levels as well. So sometimes it's useful to be able to see these unoccupied states to see what they look like. Again, they would be the states where an electron transfers to when it gets excited by a photon. So if you're doing some sort of photophysical processes, something that's like solar cells or something where a light comes in, it's interesting to know where the electron would want to transfer to when you shine the light on it. Particularly different frequencies of light would go to different states. And that defines our density functional section. Reorder this. Basically, the exchange correlation section defines which density functional we're going to use. So that's kind of a theoretical thing. And at that point, the problem is kind of specified, but then we need to do some additional numerical approximations to solve that defined problem as much as possible. And that's what the rest of these things are doing. Now, if you think about density functional, it defines given external potential, so given sort of a system, it says you can, or there's a well-defined problem of finding the best density and the lowest energy given that setup. So what we need to do at this point is to actually define physically our system that will give us this external potential. In fact, this is a little bit mixed up with the technical parameters in this one, but we need to essentially define the locations of our nuclei, and then from the electron nuclear interaction that we're going to assume, this then defines the external potential. We could define an extra external potential up here if we wanted to include, an electric field or something in the system. So in this case, it's a coordinate section. So this is basically the same as In the classical case, I've got two hydrogen atoms and I've set them 1 angstrom apart from each other, separated along the x-axis, and I'm putting everything into a box 10 angstroms by 10 angstroms by 10 angstroms. And this again repeats, but now there's 10 angstroms between the hydrogen atoms molecules, so they're not really interacting. I guess there's 9 angstroms. No. And pretty much finally in here, at least a bit that's specific to density functional, for each of these kinds, so if I had a different species, if I had a oxygen, I was going to start doing a water molecule, I'd have an extra kind section for the oxygen. Here it's got which basis set is on it, so which set of Gaussian functions will be put on top of each hydrogen, and then the overall wave functions will be some linear combinations of the hydrogens on this, of the Gaussians on this hydrogen and on that one. And potentially,
you only need the
no, carry on.
You only need the kind section if you have the density functional theory programmed in.
Yes, exactly. So for a classical problem where you've got a Lennard-Jones parameter, for instance, it doesn't need these. But on the other hand, we had to give it the parameters of the Lennard-Jones parameter interaction to tell it how the atoms were interacting in that case. So in both cases, what we're doing is defining the Hamiltonian. We're defining how the energy of the system is calculated. It's just that we've got very different flavours of Hamiltonian that require very different sort of inputs to define them.
Okay. So with these codes for the basis set and potential, where would we find, say, the codes for maybe oxygen or for something else?
What I'll do in a minute, we'll get a sort of a template that you can just use for. So in CP2K, let's get another window. I think I've got a spare one here. In the code, it comes with a whole bunch of files with sort of this auxiliary data, and it used to be a big problem, but there's some substandard basis functions for, if I remember what it for,
Hydrogen, carbon, nitrogen, oxygen, fluorine, silicon.
so it goes down to rhenium, uranium. So I remember, I think it goes down to something like atomic number 86. I think it's been expanded a little bit. So for most elements, you should be covered. And they've all got essentially the same name. So really you can just sort of copy. There's more to it. It is a parameter that controls effectively how accurately you've solved the problem. The bigger the basis set, the more numerically accurate your solution should be and close to the full solution. But for now, I think we can just always take this. So if I change my hydrogen one, there's something weird about the cut and paste bit in this. I just select and then it should be right click to. Yeah, okay. So I've now put that in. And these so-called pseudo-potentials, which define this nuclear electron interaction, that reproduce the properties of atoms. We won't go into that. It's a sort of a separate course in itself. but again, there basically all you need to do is to specify the number of valence electrons in the system. And for most atoms, that's fairly straightforward. I'm not sure if you actually need to do that. Can you just specify them? No, you can get away with that now. It's been made more user friendly. I think that will work. Let's just see if that works. What's at the bottom? So this is just doing an energy calculation for now. Let's do energy force, so we'll calculate the force. Cool. So it doesn't like that. For technical reasons. Comments don't work in names where you're actually specifying an external.
I think it's just all the comments that are working.
When I changed the basis function, it was in a different file. So there's a basis set here, a file name called basis set that contained the original file, but the one I changed it to was in this different file, so I just had to change the definition there. The reason it doesn't work is if you put the hash, the thing there is actually what I had before. This is the real technicality you don't want to know. But if I put this hash at the end of there, basis molop space hash, it is a valid file name in Linux. There's no reason why you can't call a file that. So the fact that you've got the hash, it doesn't automatically transfer to being a comment like it would in other lines. So where you're specifying a basic, an actual file name, it's probably not a bad idea to keep the comments separate anyway. It tends to be a bit easier to read. Right, let's do that again. Now I've just checked on that. Let's just see what we have here. There's quite a lot of output, and most of it's not really. I mean, it's all useful, but probably not useful for us. There's some stuff mainly about the computer, about sort of where it's found files, how the program was compiled, built, code. There's quite a nice bit at the beginning where it prints out the physical units. It tells you the dimensions of the cell that the molecule's put in. Obviously, if we're running an individual molecule, we don't really need a box to some extent, but conceptually and for practical purposes, I think it's easiest just to put it in this periodic box. Now, it tells us a little bit about the density functional calculation. So there's a bit, I'm not sure, I've got time or strength to into restricted Kuhn-Sham calculation. This means spin up and spin down electrons are the same. So you specify an energy state and 2 electrons can go into it. In principle, you can apply an extra degree of freedom and you can have one set of states for spin up electrons and another for spin down. If you've got different numbers of spin up and spin down, they can have different energies. This leads to polarization, and this gives you magnetism and other effects but we won't worry about that for now. Connected to that, we've got the multiplicity of the system, and in this case it's in a S equals 0 state, or there's no spin polarization. All the electrons are paired up. More technical parameters. Then we get some information about the basis set on hydrogen. Again, we don't really need to worry about it now, but we've got essentially for each of the Gaussians, each of the atomic orbitals that we're then going to make combinations out of, they're built up of 5 Gaussian functions with different exponents and sort of different weightings in there. More technical parameters. Then there's the guess for the atomic kind hydrogen. So this is the first thing it does, it solves the atomic problem to get a density for a hydrogen atom, and then it's going to put together those densities to form a guess at the density for the molecule from a superposition of atomic densities. And now it begins the SCF wave function optimization. So this is the bit where it takes that initial density and it goes through a series of cycles optimizing the density. You should see that the total energy is going downhill until it eventually reaches the best energy it can at that configuration of the system. There's a convergence parameter. I won't go into details of it. It's to do with how much the largest change in density anywhere in the system. And this last one is how much the energy has changed. So you can see in the last step, it's converged to what, a tenth of a microhartree. It's quite a small amount. So this is below about a microhartree. So a hartree is about 27 electron volts. So this is, I don't know, about a thousandth of KT at room temperature. It's a small number. Small technical parameters that can be very useful. So electronic density on the regular grids. I've got -2 charge of electrons, which is fine. A hydrogen atom, I've got 2 electrons. And when I'm doing the numerical work, so when I'm putting it into my boxes, onto my grids, I've got 2 electrons there represented up to 10 decimal places or something like that. It's fairly accurate. There's a little bit of a breakdown in terms of which bits are making up the energy of the system. So there's the exchange correlation energy, which is negative, because this describes how the electrons try and stay apart from each other. There's the Hartree energy, which is the classical electrostatic repulsion of the distribution of electrons. Consequently, that's positive and repulsive. And then there's self-energy of the core charge distribution. I think this is the electron-nuclear interaction. And then the total energy is a bit hard to break down. But essentially, you end up with a negative number. So compared to the nuclei and the electrons or whatever sort of set off on their own, we end up with a bound system. You can make various approximations to estimate what the charge is on atoms. What's perhaps a bit more interesting is if we look at the eigenvalues of the occupied spin. So this is the energy levels of the system. We've got one energy level at -0.26, not -0.27 hartrees. If you like, that energy level is going to have our 2 electrons sat in it. And then there are, I've printed off 5 energy levels at higher energy level, higher energies, that are empty in our system, because I've put our 2 electrons into this lowest energy. Then if I go back to my input file, I asked it to print out the forces, and you can see that this atom wants to move in that direction. It's got a force to the right on it. This atom's got a force to the left on it, which suggests to me that the 2 atoms want to move closer together.
Matt, did you say that the sort of standard units they're using there are Hartrees rather than electron volts?
And I think you can take it, everything in this output file, unless it gives brackets and units, will be in atomic units. So the units are forces, and it gives here atomic units. So that's going to be Hartree per Bohr. So the Bohr radius is the radius of a hydrogen, the average radius of an electron and hydrogen atom. So that's the unit of length in atomic units. And there's a table of these things up here. So a Bohr is 0.529 angstroms, and an atomic unit is 27.2 electron volts. That can be useful to see, or it's there in kilojoules per mole, or various things. But yeah, the default units are electron volts. It's not always totally consistent, but it's pretty consistent on that point. So let's just step back 1 second. And what we asked it to do here was to calculate the energies and the forces. So it didn't move the nuclei at all. What it did is exactly what you saw. It took an initial guess at the electronic density. It minimized that, the energy of that system, which gave me the unique ground state density, which gave the minimum energy of the system. And then it calculated some properties at that electronic density. In principle, you can then, from the distribution, you can work out the dipole of the system. You know where the charges of the nuclei are. You know where the charge of the electrons are, so you can work out electric dipole of molecules. You can calculate the excitation energy, so the energy to go from an occupied level to an unoccupied level. You can estimate charges in the system. You can do various things once you've got to that point. And the other thing we calculated there was the force. But if we change it to geometry optimization, then it should do sort of a double optimization problem. I did go through this before, but again after Friday. So it finds the best electronic density at your initial positions of the nuclei. Then, as well as calculating the energy of the system at that position, you can also calculate how the energy will change, so the gradient of the energy with respect to moving an atom. So you can take the partial derivatives with respect to the components of the positions of each of the atoms, and then you can solve the optimization problem of moving the atomic positions to their minima as well. In which case, if you go back to the one-dimensional problem, you move the atoms to a distance such they're at the bottom of the well. So that should be where the system would like to be at very low temperatures at 0K. So if I run this, I should see it sort of repeating what we've done before. It moves them, then the density needs to change a little bit once you've moved the positions of the atoms. There's a different minimum electronic density. So it minimizes that, calculates the gradients from the nuclei, moves them again, and then in a few steps it should have found a minimum. there. Like breadth max gradient. Then I can see the maximum gradient, which is the energy gradient, so that's the opposite of the force essentially. You can see it decreasing down to a point which is numerically good enough for us. We can specify that. So it's finding the distance that the atoms like to be. And we can see, in fact, the atomic positions and how they're adjusting as the system moves along. And I'm not going to do the maths, but we should get a it's going to be a very boring picture, but we should just about be able to see that the atoms are adjusting position as we move it. Select hydrogen. So as we started it off, it doesn't show the first frame, but it's adjusting the distance between the two hydrogen atoms until we reach the minimum location. And also here I've got my electron densities and wave functions. It's a bit messy. By default, it's every time I've moved to geometry, it's created those files. So I've got an electron density for the initial, for the 0th step up to the 8th step. And then for each of the 1 electron cone-sham orbitals, I've got from 0 to 8 of the first state, 0 to 8 of the second state, and so on. So if I wanted to change my system to run to a water molecule, what would I need to do? So this stuff up here, technically this should be increased, but I think we can get away with it. All this stuff is going to stay the same. This is kind of a recipe for how I set up and solve my nonlinear problem. So if I'm keeping the same exchange correlation functional, then all of this stuff should basically be able to stay the same. This one setting here, this multi-grid, which is a technical CP2K setting, is actually slightly dependent on the type of atoms. And this will be a bit noisy with that setting. Increase that to 600. But apart from that, more or less all I should have to do is change the coordinates. Let's see if we can cope with this. So now I've got 6, an oxygen by that in a linear chain, which isn't really what we want. I'm just going to shift those two atoms off being completely linear. So if they're completely linear, there's a weird thing where that might be an unstable equilibrium position of the system. So just for argument's sake, I'm going to shift it like that. Does that make sense? I've added in the extra oxygen atom, and I can go and look on the internet and find a much better initial geometry for this system. But let's see if that's good enough to get us there.
Yeah, you need another claim statement, don't you?
Yep. And I now need to define this for the oxygen. And actually, this will work because these two definitions don't have anything atomic specific. I mean, they are specific in the input file to the atomic types, but for each atomic type they've been given the same name, so I don't need to change anything there. Got forces, I'm doing my geometry optimization. I'll be good and remember to change the name of my project. It is a good practice to call things useful names. What I'm going to do, just to avoid how many hours in symbolic do you reckon?
Wait, how many? What's symbolic?
How do you spell symbolic? It's always...
Yeah, that's correct.
Because I don't know if you saw in the last one, with every step I was getting all these output files. So this just means -1 means don't output it, but just write a final one at the end once it's done everything. So that's unnecessary, it's just a... This is a bit slower because I've changed that grid setting there. But you can see now that the energy's going smoothly down. Should, after the first step or two, be. The initial geometry was absolutely terrible. I mean, it was complete nonsense. I put in. Sort of take it a minute or two to sort itself out. It's amazing how long it takes when I'm just wittering at stuff, isn't it? I apologise, it's very long-winded stuff. I think we'll take a break in a second.
I don't know why, but it appears to be doing the same thing over and over again.
So what it's doing, let's just have a quick look at that, and then it is doing the same thing. I mean that's what you want computers for, yeah. Doing the same thing again and again, but not quite. So what we do is we optimize the wave function. So we get some initial guess at the electronic density, and then we solve the problem to get our eigenvalues. We get a new density. We repeat through. There'll be, I think, a bit more detail in the lectures I linked. And eventually it converges, and we've got the minimum density, or the density that corresponds to the ground state that gives us the lowest energy of the system, given nuclear positions. And now what it's starting to do is doing a geometry optimization, which is moving the atoms to find the best location for the atoms to be in. So now it does optimization step 1. It moves the atoms. It does like a Newton-Raphson sort of method for finding the roots of equations, the minima of equations. But now it's doing it in a multi-dimensional problem, the partial derivatives with respect to all the atomic positions. So it guesses where they've got to be moved to, the best location that will make the gradient 0. Now, once we move the atoms to a new position, the external potential has changed, so there should be a new ground state density and a new energy. So it redoes the calculation, finds the new best density, new best energy, and then it takes the partial derivatives with respect to all the atomic positions and sees if they are close enough to 0. We can see, in fact, from the forces that we've still got some fairly significant, but much smaller, in fact, than the first step, forces on the atoms. And actually, we've got some indication here that the total force is quite well described, so it's reasonably accurate. And then it repeats that through several times. So it is doing the same thing, but it's doing a minimization where it's finding the best position of the atoms. There. So after 4 steps, it's now got to a point where the forces on the atoms are accurate enough for us to consider them to be 0. For a proper calculation, you might want to be a little bit more accurate. And then it just recalculates things at ground state, and it's calculated the energies of the occupied states, so the ones that the 2 electrons are being fed into, and the squared, sum of the squares of those densities gives the total density of the system, and the energy levels of the thing. And there's a HOMO-LUMO gap, so the energy gap between the state with an electron in it and an empty one, so an approximation to the photon energy you would need to excite it, which is about 9 electron volts in this case. So that's high hard UV energy, which explains why water would be transparent, because it requires a photon of 9 electron volts to get the electron from here up to the unoccupied state. And we've got these there, so now let's copy this H2O. Let's get one of these wave functions just so we can look at it. Then we'll take a break. So I had 5 unoccupied levels, 1, 2, 3, 4, 5, and then so if I load in that one, not sure if it's done what I wanted. No. So I didn't distort it enough, and it's found a linear water molecule, which is a rather peculiar thing. However, it is a local minimum. Well, it's an extremum on the potential energy surface, which means that the gradients, the partial derivatives with respect to all the atoms are 0, at least numerically, in this configuration. So it's actually probably at the top of a hill as it goes from being like this to being like that. So if you want, you can mess around, put in some slightly better starting coordinates and try and get a V-shaped water molecule. because this water molecule would, if this was ground state, life would cease to exist on the planet, because this being symmetric wouldn't have a dipole moment, so water wouldn't be anything like as sticky as it is, would have a very different boiling point, and everything would change from there. Do that bit again. Let's just load in the wave function, just have a quick look at that, and then we'll take a break, and then I'll talk a little bit about, just very briefly, hopefully I won't be another hour. I really don't know how I talk for an hour. I don't consider myself a particularly verbose person, really. It's what it is. Here we go. So that's the that's what the so-called highest occupied molecular orbital looks like. So if you were to shine light at it, the lowest energy transition would come out of an electron state whose wave function looks like this. Square it to get the electron density associated with that, and it would go up to the next energy level. Okay, any immediate questions on what I've just been through?
Are you able to show us in a little while just what files you loaded into VMD?
Yep.
To generate.
What I'll do is I'll
before we were just putting the position file in where you put two files in there, position file and
yes, one of these cube files. So I'll go through that. I'll upload them in a second onto.
Obviously, watch these back and just do that for myself. But it's just,
yeah,
it's just those little niggly things that you're trying to recreate something with VMD.
Yeah. So the one I loaded up with this. So there's project name, and then it gets WFN, short for wave function, and then it's got a number, and it's a cube file. This is the one I loaded in. You can see there's this one here. Then I created two representations, which are isosurfaces at plus and minus 0.005, and in this case is actually, I think it's electrons per cubic Bohr. I'm sure it's electrons per cubic Bohr, but it could be angstrom in that case. Electrons per unit volume. And the reason why, just to finish off this bit, why I printed that out was in the DFT section I've got two print sections, one for the total electron density, and so I get a total electron density cube file. So it is basically a scalar field. It says that this, in this little cube, the density is this, the next cube is this, then that. I mean, that really is literally what the file is, a list of the densities in these different sort of strips across the thing, and then the same for the wave function. And that I got from this so-called molecular orbital cubes file. and by default it would print them out every time it moved the atoms, but I told it to only print it out in the very last step. Logic. Try and put something up on Blackboard. Any other questions before I sign off, and then perhaps we can reconvene at past?
No, not from me.
Is 2:30 too long, or 1/4 past? 10-minute break? What's the best?
10 minutes should be fine.
Okay.
I've got no problems with it.
Okay, I don't want to. I mean, not that I want to deprive you. I can, witter on for hours it seems, but I'd prefer to try and be a little bit focused. Right. I'll stop recording this now, and